Okay, hello everyone and welcome back to Chemistry 3120. Today's lecture 4, and today we're going to be focusing our time on reductions and oxidations. So reduction and oxidation reactions are some of the most common type of organic transformations. With respect to organic chemistry, a reduction typically involves the addition of hydrogen atoms to something like a double bond, and oxidation typically refers to the removal of hydrogens and the addition of oxygens. All right, so these are often referred to as redox reactions. So redox reactions in organic chemistry typically refer to, as I mentioned, the addition or removal of hydrogen and oxygen to carbon atoms. Okay, so in terms of reduction, I'll give you sort of a classic example where you might have a double bond like this, and then if you want to reduce it, we're going to be adding hydrogen across this double bond here. Okay, so we can think of hydrogen, I just put those in quotes. What this really corresponds to is a source of 2 protons plus 2 electrons, and that will give you your particular product. So this would correspond to reduction. And an example of oxidation might be something like taking a fully reduced compound, something like methane as an example, and we can undergo different levels of oxidation. So if we oxidize this, we can add 1 oxygen atom to this molecule and remove a couple hydrogen atoms. This will give us this molecule here called formaldehyde, and then we can further go another reduction, or sorry, another oxidation, remove 2 hydrogen atoms, add another oxygen, and then we're left with carbon dioxide. So as I mentioned, this is a very common type of transformation that's used in organic chemistry. What we're going to focus on today is reduction, and later on in a few lectures we'll talk about oxidation. Now reduction comes in a number of different flavors and forms. So there's 3 main types of reductions. So there's something called metal hydride reductions. So this is things like lithium aluminum hydride as an example, sodium borohydride. Okay, these are metal hydride reducing agents. Okay, and you've seen some of these examples in second year organic chemistry. Another type of reduction is catalytic hydrogenation. And this could be either a homogeneous catalyst or a heterogeneous catalyst, typically involving H2 over a catalyst, and then this metal catalyst is able to reduce usually a double bond. So you have seen things like this before, like hydrogen over, for example, a palladium carbon catalyst is an example of catalytic hydrogenation. And then the third type is a type that you may have not seen before, but it's called dissolving metal reduction. And if you look at, if you break apart what the H2 is for reduction, it's comprised of a proton and 2 electrons. So in this dissolving metal reduction, what researchers will do is they will use free electrons and protons as their source of reducing agent. So often what researchers might do is they will take things like lithium, in its native form, so it has a free electron. And for example, lithium and ammonia is a great way to do a dissolving metal reduction. So what we're going to focus on, or start at least today, and we'll probably do 2 or 3 lectures on this, is metal hydride reduction. Then we'll talk later about catalytic hydrogenation and dissolving metal reductions on future lectures. All right, so let's talk about metal hydride reductions. So before we do that, let's think back and examine carbonyl structures and ask which ones are more susceptible to nucleophilic attack. So perhaps I'll draw them here. So recall we had aldehydes, ketones, esters, and then we would have amides. Right, and you've learned that these two here are the most electrophilic, whereas these ones are less electrophilic and more stable. We just finished the protecting group unit where these two would require protection the most as an acetal or a ketal. So when we're thinking of reduction using metal hydride reductions, a very common type of reduction involves reducing these types of groups: aldehydes, ketones, also esters, and also amides. And we're going to examine how this will actually function, how this will work. But as you can see, the ones that are most easily reduced will definitely be the aldehyde and the ketone. All right, so metal hydride reduction. So a metal hydride is a particular species that contains a metal atom. So in this case, lithium aluminum hydride. So the aluminum will be in a negative state coordinated to a positive lithium, and the hydride, the H that comes from this reaction, is a nucleophilic hydride source, so H minus. So this is lithium aluminum hydride. Sodium borohydride would look something like this. And these are 2 classic examples of metal hydride reagents. There certainly are some other ones that we'll look at as well. One of them is called Dibol, which stands for diisobutyl aluminum hydride. So often abbreviated as Dibol H. Okay, but what you can see is that they all have these hydride nucleophilic forms that can act and attack, in this case, whatever carbonyl group that we're interested in reacting it with. Okay, so let's start with lithium aluminum hydride. All right, so lithium aluminum hydride is it's a very strong reducing agent. But I want to show you how it works mechanistically in terms of its ability to reduce. So let's start with aldehydes. So let's start all the way on the electrophilic table with carbonyl groups and start with the aldehyde. Okay, so here's your aldehyde, and what I'm going to do is I'm going to draw the lithium aluminum hydride, and I'm going to draw it this way. Well, in the same way I've drawn it on the other board. Okay. So you know that this here is your electrophilic carbonyl, and these hydrides are negatively charged nucleophilic sources. So the way that I like to show reduction happening is that the way you can explain it is that the aluminum is actually a fairly electropositive element, and it's actually not super happy being negative. So it's very happy to release off and react that H- onto the carbonyl derivative. Okay, that's why it's so reactive. So in terms of how to show this mechanistically, I like to show the bond being broken, and again, showing the electron pairs coming up through the hydrogen atom and attacking this aldehyde derivative, this aldehyde right here. So if we do that, we're going to end up with and this will be your new hydrogen atom that has reacted and attacked. Okay, so at this stage here, you have your O-, this alkoxide unit, and this is actually going to coordinate with the lithium that is used to counterbalance the aluminum. So once this comes and reacts, this aluminum will now be neutral, and this no longer complexes with the lithium, so there's a strong tendency for the oxygen and lithium to come together. And now keep in mind that we have aluminum, not tetrahydride, but we have aluminum trihydride. And then what's going to happen is that we're going to get transfer of the electrons from here to the aluminum. Keep in mind too that this oxygen-lithium bond, I've drawn it as a covalent bond, but it's really in fact a strong ionic bond. Okay, you have the O-, the positive lithium. So this is quite labile, and then what will happen is our lithium plus will get released off, and you'll transfer that to the aluminum. Now, keep in mind your aluminum has 4 bonds again, so it's now going to be negatively charged. So this sits in solution for some time until you do something called a quench. So what is a quench? So a quench is something you add to a reaction to finish a reaction. In this case here, the researcher would add a solution of water very slowly to this reaction to quench any remaining lithium aluminum hydride. So here is water or some kind of proton donor. You could also use something like an alcohol. And essentially what's going to happen is you're going to release off that aluminum trihydride and then transfer that proton to that alcohol, and there's your product. We've gone from an aldehyde to an alcohol. We've reduced it. So the overall net reaction for this, or how you could illustrate this, is you can take an aldehyde, and you often see this drawn as lithium aluminum hydride, and then often number 2, you might have a workup step. It's important to note that there's no water added at the beginning of the reaction. Okay, it's only done near the end of the reaction to stop the reaction and to liberate the oxygen-aluminum bond from that coordination. Okay, so that's how we do that for aldehydes. Let's take a look at something like an ester. So aldehyde ketone is going to react very, very similarly to that. The only difference is that the H is going to be replaced with an R group. Okay, so if we look at an ester, let me draw it up here. So esters are a very ubiquitous functionality. They're used often in organic synthesis. So if we have an ester here, and we want to reduce this, we can certainly use lithium aluminum hydride. Now, keep in mind, the lithium aluminum hydride is very strongly nucleophilic, but in terms of the electrophilic strength of the ester compared to the ketone and aldehyde, it's much weaker. It's not nearly as electrophilic compared to these two. And you know that because you get strong resonance donation from this oxygen here into the system, thereby making that less electrophilic. So in order to make this a better electrophile, recall that you have lithium plus in solution. So the oxygen, the lone pairs from the oxygen, will actually coordinate and activate that ester, as I'm showing here. You now have this positively charged oxygen. This is now a really good electrophile. So now your aluminum, your negatively charged aluminum, can now act as an appropriate reducing agent and start to reduce the ester. So let's take a look and see what that looks like. So this is going to come and react analogously to how it's shown back over there. So if we do that, you're now going to have a structure that's going to look very similar to this. That's your structure there. So one H minus has gone and attacked. Now, at this stage here, let's think about what could happen next. In some ways, you have something that resembles like a tetrahedral intermediate after it's been attacked, after carbonyl has been attacked. And essentially, that's exactly what's happened. So what can happen is that you do have these lone pairs. These could come back down, and then you have this OR prime that could depart. So if we do that, we are now going to be left with this structure here, which looks just like an aldehyde with the lithium coordinated to it. So my question to you is, are we going to take the ester and are we going to stop at the aldehyde with lithium aluminum hydride? And think of the electrophilic strength of that. This is now, the compound that we generated is much more electrophilic than this one. So once this gets reduced to the aldehyde, we don't have a choice. The lithium aluminum hydride is now going to also reduce this molecule too. So what's going to happen is you're going to get another molecule. This is going to come and almost immediately just react because it's just so electrophilic. Okay, so you can see that we've gone from an ester. We have 2 hydrogens attached here. Also keep in mind too that we've released off an alkoxide. And then once we make this molecule here, this is going to behave very similarly to what we had over here, right? Transfer of the aluminum trihydride, and then quench the reaction, and then you'll generate your alcohol. So let's do exactly that we're going to have AlH3 in solution. So we're going to transfer that to the oxygen. Aluminum is negatively charged. This sits around for a little bit until you quench a reaction. So when you quench a reaction, we're going to add a proton source. Typically we add something like water. And then this O will transfer and pick up a proton. So you are left with your alcohol. So that will be your final product. So in terms of a complete reaction, we could say lithium aluminum hydride, and then step 2 is that water quench workup. And that will generate your alcohol. All right, so you can see a bit of a pattern here. We've looked at aldehydes, ketones, same esters. So the last thing we need to look at for this series are amides. And you might be saying, okay, well, it looks like they're all leading to primary alcohols. Let's take a look at the mechanism and see exactly what's happening. All right, so here's the big question. What happens when we take an amide bond, react that with lithium aluminum hydride? What is the product going to be? Okay, so amides are very stable, not very reactive. So what you're going to have to do for sure is you have to coordinate this to the lithium, just like we had seen with the esters. So you take your amide, activate it with the lithium, and now your nucleophilic hydride source can now come and attack. So maybe I'll do this one in color, because using colors is fun. All right, so let's make this red. So when this attacks, this will come up here, and we will have and here's our new hydrogen atom there that I've drawn in red. All right, so what's going to happen next? So like we've seen before, you have this thing in solution, so you're going to get the transfer as we've seen with the other functional groups. And you might be saying, okay, I see the pattern here. We've done this is the third time he's doing this. And you're probably going to say, okay, this is going to come down. We'll kick this off. It's going to be an aldehyde. And then you reduce that aldehyde to an alcohol. So no matter what functional groups you have here, whether it's an aldehyde, ketone, ester, or amide, they all end up as alcohols. Or is that really the case? Now, I want you to compare the electron donating properties of the oxygen and the nitrogen. So in this case up here with esters, we both had oxygens here, okay? And the reason this came down, this left, was because, well, this is obviously a much better leaving group compared to O lithium or O2 minus, which is essentially impossible. But in this case here, we have two different things that could happen. You could have potentially the oxygen coming here and kicking this off as your leaving group to give the aldehyde. That's one scenario. Or another scenario is that actually the nitrogen donates electrons and this gets removed. So which one is it going to be? And how do we know? So let's think back to our electronegative table, right, that we've looked at a few times already, right? So if you go from left to right, electronegativity, you're comparing nitrogen and oxygen. So oxygen is more electronegative, nitrogen less electronegative. Which one is more willing to donate electrons? The nitrogen, right? It's a better nucleophile. It's more willing to share them. So if you think of just the electronics of what's going to happen, the nitrogen is going to win. It's going to be stronger in terms of its ability to donate electrons. So this is going to form a double bond here. And the oxygen says, you know what, that makes more sense because I'm more electronegative, so I would rather actually accept that electron density. So what you end up generating is this intermediate here, which now looks very different from an aldehyde. Okay, so we have this imine here. We actually have a positively charged nitrogen right over there. And this is actually called, it's an amine, but it's called the iminium ion. And this thing, as you can imagine, is actually really, really electrophilic, right? You have electron density moving to the nitrogen, a positively charged molecule. So this right here is the electrophilic center. So is this going to be your final product? Well, keep in mind that we have a lot of this lithium aluminum hydride present. So we have, this time I'll use green. We have this molecule here. And this thing is going to be very nucleophilic towards this electrophilic carbon. Push electrons to that nitrogen like I'm showing. If you do that, you are going to generate with two different hydride atoms that have reacted. Now I've just drawn them in color so you can see exactly where they're coming from. So this is not an alcohol. Our final product is not an alcohol. In fact, our final product is an amine, right? So we've gone from an amide to an amine. So in terms of our final reaction, you can see here this is our final reaction. Now, at the end of the day, you still have to quench any excess or remaining lithium aluminum hydride, so we will, of course, do that water workup step. But in terms of mechanistically, in terms of its role with workup and generating the product's formed before the workup step. So that's how you make that compound. All right, so just to reiterate and just to emphasize, this does not happen. The oxygen atoms will not come down and release off NRH minus. nitrogen is more willing to donate electron density compared to the oxygen. Okay, so all right, so you can see that lithium aluminum hydride is pretty strong reducing agent. It reduces all these different functional groups that we've looked at. And you might be saying, well, is there something a little milder that we can use? And definitely, we're going to look at sodium borohydride. One of the things too about lithium aluminum hydride that you should be aware of is that it is a really strong reducing agent, and you have to handle it with extreme care. It's a highly exothermic reaction when you add it to any type of material, and there is a great risk of it igniting. So you have to be, it's super reactive. So sometimes it's not very practical. And furthermore, it might not be practical if you have a molecule that has aldehydes, ketones, esters, amides, and maybe you only want to reduce one or two of those functionalities and not all of them. So let's take a look at a gentler reducing agent. And this is called sodium borohydride. It's a milder form. It's a milder reducing agent, not as violent and rigorous. Compared to lithium aluminum hydride. And let's draw the structure. And compare that to lithium aluminum hydride. Okay, so here are your two different hydride reagents. You might say, well, they look fairly similar. I can see that we have a boron here. This could act as a negative hydride source, as a nucleophile, and yes, you are indeed correct. But why is this one less reactive compared to lithium aluminum hydride? Okay, so let's take a look at the electronegativity of boron and aluminum. So it turns out that the electronegativity of aluminum is actually around 1.5. All right, boron is around 2.0. So they're definitely not electronegative elements. They're certainly nothing like nitrogen and oxygen and fluorine, right? If you look up there. But if you compare these two directly, you can definitely make the argument that aluminum is the more electropositive element, and boron is less electropositive. Boron is more electronegative compared to the aluminum. So the other way I like to say this is that the aluminum is more willing to lose that negative charge because it's has very low electronegativity. Therefore, it's more reactive. Whereas the boron is more electronegative and therefore is more stable in a negative form, so less reactive. And furthermore, if you're doing reactions with sodium borohydride, you actually typically do these in a protic solvent with things like water or methanol. Whereas with lithium aluminum hydride, when you're doing those reactions, you're actually doing those under very anhydrous conditions. You can't have any water present at all, because what you'll do is you'll start to pick off one of those protons and generate H2 gas, which can be, if you have too much of that, that's an explosive gas, and that could be quite dangerous. However, these, like I said, are typically done in water or alcohol. So let's take a look at the reduction of an aldehyde using sodium borohydride. So if you actually take sodium borohydride and if you really don't perhaps use water or methanol, you might not get this reaction to work as well as you would like. So how does the water and the alcohol play an impact? Well, one of the things that's thought to believe that to happen is that there's this hydrogen bond network happening where you get some partial activation of this carbonyl group to nearby hydrogen bond donors from something like water or alcohol. So that helps to push the dipole here and make that more electrophilic. In addition, you have now your sodium metal that it can also coordinate with. So this is necessary to activate the aldehyde or ketone so that you can get nucleophilic hydride attack occurring, like I'm showing you here. So once you do that, it's fairly straightforward. You generate this alkoxide, and then because we are in a protic solvent, either water or methanol will transfer a proton to the O-, and you'll generate your alcohol. Okay, so that works for aldehydes, would work the same type of mechanism for ketones as well. But where sodium borohydride distinguishes reactivity between different carbonyl groups is at that ester functionality. So here's your aldehyde, here's your ketone. So I'll just put a little check here. Works well, reduces well for both of these. If we have an ester, it's not very reliable. Okay, I'm not going to say it doesn't work, okay, but it might be very sluggish, it might work very slowly, and it might not be very robust. So, so what we'll do is we'll put a little X through here and we'll say reacts very sluggish or very slowly. And that's the ester. So the ester is, as you know, less electrophilic compared to the aldehyde or ketone. And then furthermore, if we look at our amide, this one here will not react. Okay, the amide is just too stable, not electrophilic enough. So sodium borohydride is often used in situations where you want to reduce perhaps an aldehyde or a ketone, but you really don't want it to also react with amides or esters, whereas lithium aluminum hydride would react with all of them across the board. Since this chapter is focused on chemoselectivity, what we're going to unravel over the next couple lectures are different reducing agents in different conditions to be able to selectively reduce our particular functional group. All right, so there's your introduction to metal hydride reductions. See you next time.